Okay, you're participating in the DCW Asia conference, I think in a couple of ways. And maybe
Mm,
first up, we can look at the fact that you're leading a panel session
mm.
on sustainable tropical data center testbed phase two. So yeah, just give us a bit of an overview and then we'll sort of drill down a bit. So.
Sure. Yeah. So phase two of the Sustainable Tropical Data Center Testbed is a living lab for AI native grid interactive data center in hot and humid climates, like what we are experiencing here in Singapore. So we are moving beyond component demos to integrated vendor neutral system trials. Right. For example, we'll have liquid cooling across different form factors, zonal or distributed heat rejection, seawater, the cooling or seawater heat rejection, the where applicable, as well as a hybrid AC/DC the power infrastructure, right? Then coupled with flexible demand response operations, as well as safety and ESG guardrails. So the goal that we are trying to achieve is actually to turn promising ideas into validated bankable practices for the data centers owners, operators, financiers, especially for AI densities that pushes 100, 600, or even 1 megawatt, right, per rack today and tomorrow.
Yeah, so I mean, as you've outlined there, I guess the simple equation these days is the rack densities required by these AI workloads mean
Mm,
that the full stack in the data center needs to be
mm,
pretty much reimagined. And is that,
mm,
I guess, difficult for data center folks to get there? Because normally
mm,
there's little incremental changes, but this requires almost a full
mm.
rewriting of the rules. Is that right?
Yes, the entire the stack, as you rightly point out, all the way from device to package to cold plates, rack manifolds, or even the white space, hydraulics, airflow, facilities, water loops, power infrastructures, controls, and grid interface, right? AI, the accelerators in particular, like NVIDIA, the GPU are rated having the DP at 1.4 kilowatts level. So it invalidates the legacy air only the assumptions. So we have to really look at thermal design, electrical distributions, including high voltage DC backbone, structural loadings, water stewardships, and operational workflows must be actually reimagined, right? The word that you rightly used. Treating cooling as an add-on is no longer viable.
Okay, and during the discussion, I think you'll be looking at the field results
Mm,
from the open vendor neutral test bed. There's plenty, I guess, to discuss, but I
mm.
mean, one thing I think you've got is distributed or zonal cooling. So perhaps you can tell us a little bit about what you've discovered there.
Yes. So rather than pushing all heat to a single plant that is actually conventionally done, so we will evaluate the zonal strategies such as rack or row CBUs, rear door heat exchangers for air assisted liquid cooling, modular heat rejection blocks, as well as distributed topologies, right, which can actually improve the turn down efficiency, the fault isolations, the retrofitability, as well as to allow differentiated SLA, right, per hall or pod. And this is actually especially important, right, when AI and non-AI, the workloads actually coexist within the same white space.
Okay, one of the other potential, as I suppose, upsides is the opportunity to use the rejected heat, the
Mm,
waste heat reuse, and also I think you've been looking at water because you know
mm,
people are always concentrate on the
mm,
power aspect, but clearly data centers consume quite a lot of water, so water
mm,
usage effectiveness as well. So perhaps tell us a little bit about the waste heat and the water side.
mm. Two priorities. First, waste heat, right? So liquid cooling actually gives higher grade waste heat suitable for heat to X, right? So and X can be anything, right? From domestic hot water, absorption chiller, industrial preheating, or even the low temperature, the district network, although not quite viable here in the tropics, but certainly a lot of relevance in the temperate climates. So we are mapping the use cases that are the realistic, right? Based on the locality, right? For example, in apex cities may not be a case of for district heating, but it can actually recover, for example, the waste heat for the regeneration or desiccant dehumidification systems, or I can use it to potentially even regenerate for direct air capture systems. right? Second, then for specifically for water, we actually emphasize the adiabatic free or adiabatic minimize operations at warm water set points and the non-evaporative heat sinks or heat rejection so as to drive down WUE, right, while keeping resilience up. So where evaporation is unavoidable, which is typical for the tropical climate, we can actually look at innovative heat rejection strategies, right? Including rejecting to water bodies, right? Including seawater. But obviously, this will be actually very the site dependent. But obviously, we also need to make sure that we adhere to the environmental the safeguards. So I think that it's really an opportunity for us to really reimagine, right? The entire stacks, right? How do you perform cooling? How do you do heat rejection? How do you recover waste heat for productive purposes? So I think the future is actually challenging, but at the same time, I think it opens up a lot of opportunities for innovative solutions.
Yeah, and sort of following on that theme, I guess I think the project's also looked at green energy
Mm.
integration. So yeah, please tell
Mm.
us a little bit more about what you've looked at there.
Yes, I think for the longest time, the cooling and power, I actually done somewhat in the silo, right? But I think with AIDC, we're now seeing a cooling and power coming together. In fact, being co-optimized. Right? So we actually test the hybrid AC/DC architectures on-site, the PV storage, flexible fuel, the fuel cells, or gas generator options, and participation in the demand response. So the point isn't to just lower PUE, right? It's actually lowering the system carbon, right? For example, the CUE, right? Better reliability for the grid as well as fewer peak imports. So constrained the grids in APEC and elsewhere in the world, AI ready the DC must be a good grid citizens.
Again, as well as the data centers, if you like, being the home for all this AI, there's the opportunity to use AI to better sort of control, so dynamic, smart control of the data center environment. So what's happening, what's possible when it comes to using AI
Mm.
to optimize the data center environment?
Yep. So apply the physics informed and data driven control to tune the set points, flow rates, right, as well as the associated pump fan curves in real time at the rack or row levels, right? Controllers that responds dynamically to workload, right, as well as transients. And at the facility level, right, we can actually co-optimize with weather, with tariff, as well as grid signals, right, including availabilities of renewable energy. So the intention is really to link the thermal hydraulic the states with predictive models, right? So that the system can anticipate rather than just passively react.
Okay, and I think as you mentioned at the start of the conversation, the overall objectives being to sort of demonstrate how technical wins can become sort of
Mm.
bankable data so that data center owners and operators better understand, I guess, the whole sort of life cycle from design, interoperability, and the metrics best suited for AI data centers. So yeah, I suppose it'd be interesting to know where are this is phase two. So
Mm.
what else, where are you in the overall sort of project, if you like?
So I think it's still a work in the progress. I think progressively we're actually converting lab to fill the deltas into bankable the artifacts, right? And we'll be actually verifying the performance bands, right? The interoperability matrices, right? As well as some of the safety and MTTR playbooks, as well as the finance grade M and B. So beyond the PUE, WE, all right, certainly for phase two, we'll be actually reporting holistic matrix or baskets of matrices that will actually include like CUE, which we discussed just now, and even the ERE, right, the energy reuse effectiveness, the water risk adjusted indicators, right, as well as the load flexibilities, right, it takes into account the megawatts, the RAM rate, as well as the hour, the shifted, as well as reliability matrix around the liquid component. So I think what we want is actually to have the evidence stats, right, that investors and boards actually needs, right, before they make their decisions.
Okay, and then the other sort of string to your bow, if you like, at the event, you're also covering advances in two-phase direct-to-chip liquid cooling. So, um, I'd be good, I suppose, if you can talk us through some of the
Mm,
advances in terms of what they are and the improvements that they are,
mm.
potentially delivering in the data center.
Yes, certainly. So with thermal design, the power going through the roof, I think that we have really very little option, but start to look at the two-phase direct to chip or even two-phase immersion cooling the solutions, right? So for example, if we look at the two-phase immersion cooling, we can actually look at the ways to enhance the nucleation the surfaces. For example, the use of additive manufacturing, which traditionally is actually an issue, right, for most application, but with the high surface roughness that can actually generate the additional artificial nucleation side, which has served to enhance the performance of two-phase immersion cooling. But we can also look at, for example, the unibody, the leak proof or leakless cold plate design, right? Because again, with the CPU, GPU chip being the largest big ticket item in your white space, you want to actually protect your investment. You want to not have any possibility of leakage if at all possible. That's why I think such innovative solution actually will have a lot of potential. But then also obviously as we sort of design and operate liquid cooling system, we also have to make sure that the working fluid that we're using are actually the low the GWP, right? As well as with looking at smart vapor management to avoid instabilities, right? If we are going into the two-phase route. And for AI packages with extreme heat flux non-uniformity, two-phase can potentially deliver the high heat transfer coefficient at the low flow of pumping power. And that's how you get the physics of materials and the control together, right? So as to deliver a stable two-phase cooling system while meeting your next generations of heat dissipation needs.
Okay, yeah, and I think the objective of the presentation, as I understand, I think you say is to connect device scale boiling physics to facility scale outcomes. So yeah, sort of tell us how you get from the one to the other if you can.
Certainly. So we'll be linking the physics, right? For example, the boiling curve, the surface engineering to the rep delta T, right? The CDU sizing, the pump curve, and ultimately the plant choices, right? Are we going to use dry cooler? We're going to use cooling tower. Are going to use a seawater heat rejection, right? And we are going to link, right, the delta T bit, the millikelvins or the millibar, right? The delta P, the pressure, right? Decision at the cold plates, right? And actually that can why because it can actually translate to hundreds of kilowatts at the plant, right? Especially with the hundreds of megawatt capacity in time to come gigawatt data center we're talking about. Hence, that will actually allows the operator to have the line of sight, right? How the two-phase actually stop being exotic and start to become an economic design variable. Obviously, a lot more work needs to be done. Hence, I think that the platform actually allows the academia researcher to work alongside the industry practitioner so that we can actually fast track the scaling up, fast track some of the integration issue, right? So that we can actually arrive at a state whereby we can operate such two-phase system in a safe and reliable fashion.
Okay, and maybe just sort of to finish up, it'd be good to have your thoughts. I mean, clearly it's a time of great change in the data center space, thanks to the AI explosion we're witnessing. I suppose the obvious question is how can the industry
Mm,
both sort of provide the increased power that AI requires, but alongside sort of meeting climate change sustainability goals. I suppose so.
mm,
Yes, first, how much of a change are we witnessing? And B, can we manage the power demand and the sort of
mm,
sustainability imperatives equally well, or does something have to give, I suppose?
mm. I see four changes or four shifts, right? First, actually, the liquid first infrastructure, right? As the default for AI, the white space or AI data hall, right? With air retained as a comfort or a backup layer, right? Second will be the grid interactive, the DCs, right? That plans for constrained capacity, right? For higher voltage distribution, which we discussed earlier, right? On-prem generation coupled with storage as well as contractual flexibility to shape demands. And third being the thermoelectric integration, right? The waste heat valorizations where the urban forms allows seawater or the water bodies heat rejection, which we discussed, right? Which is the obviously dependent on the location, site conditions, as well as warm water set points, right? To cut water use, right? And lastly, the evidence-based standardization, which I think is important, right? The such open safety anchor liquid cooling standards, right? Interoperable quick disconnect ecosystems and finance grade KPIs beyond the PUE. I think once there's actually clarity, that also actually allows the industry to be able to design and operate the next generation AI data centers, right? With the kind of efficiency, with the kind of reliability, and the kind of resilience, right? While meeting our net zero commitment.
Excellent. And maybe just finally to finish, it'd be good to understand the relationship you've got with the DCW Asia event. I think you're a
Mm.
regular attendee. I mean, what do you get out of the event? And I suppose, is there anything in particular you're looking forward to from
Mm.
this year's show?
No, I think so that is one of the biggest platforms to really actively engage the industry players, the who's who, right? To sort of understand what are some of their the considerations, what are the pain points, what are some of the challenges that they're facing, right? And to then rally the researchers, right? To actually work on very industry relevant and targeted research so that we can actually really fast track the R&D outcome into innovative solution that will actually benefit the industry while we actually address the carbon constraint world. Yeah.
Okay, and to that point, I mean, just following that up, do you think the industry, because the industry is fairly sort of traditional and
Mm.
conservative for obvious reasons, because obviously they're,
Mhm.
mission critical, so they don't want to, have downtime. But do you think that the mindset has to change slightly because of the things we've discussed? So they will have to
Mm.
move at, as you're saying, fast track a few times. So the
Mm.
pace of change has to pick up. Is that fair?
Yes, I think so for sure the pace has to the pick up, and I think it really is all hands on deck. And I think in this regard, the government actually in fact have a big role to play, right? For example, if the government were to actually either encourage or even the compel, right, the industry to look at non-traditional location, right, for them to set up the new facility where there's actually abundance of the renewable energies, right, and maybe even mandating data centers to report their energy consumption and their carbon footprint. I think that can goes a long way, right, to steer the industry in the right direction. But again, going back to my earlier point, that it has to be all hands on deck, and it has to be a highly collaborative process. Yes, no doubt, it's still a conservative industry, but if I think everyone is actually committed, I'm actually very hopeful that the future will be a bright one.
Okay, I mean, it's been fantastic to chat, and thank you so much for sharing some many brilliant insights. So, Professor Lee, thank you so much for your time. Thank you.
Hey, thanks so much.